Now that we've gone through the pain of driving the Kalman filter, here it is on one chart, including the system model. It works on a discrete time state space system with these random process inputs and, well, process noise and measurement noise, and they are random processes. And all we assume about them are the first and order second statistics. Um, with the first order, the means being zero, and they are white, or since it's discrete time, independent sample to sample. These noise sequences are independent sample to sample. That's the model. And then the Kalman filter told us how to optimally estimate the state, this state space animal, how to optimally estimate the state and the error covariance of that estimate. How to, and then how to propagate your estimate from one time step to the next, or actually even more broadly, how to project it into the future at all. But we normally work in chunks of time. So we go from one time step to the next. And then once we get a new measurement at time step K, we update our estimate. Come up with this Kalman gain, and then we update the estimate and that covariance matrix. Let me say a few things. So what we'll keep about our estimate is its first and second order statistics. Will be zero mean, and we know its covariance matrix. So we have first and second order statistics going in, first and second order statistics coming out. And the way we derived it, we imposed unbiasedness and linearity. See, we don't know the actual probability density functions of these random process, random sequences. And we don't know the probability density of our estimate. However, if these errors are Gaussian, the Kalman filter is the overall optimal filter, not just the best linear unbiased because we imposed it. It just naturally came out linear and unbiased. And our estimate will be Gaussian as well. So if everything's nice and Gaussian, it's even better than this. Let's see. If you have no process noise, this W isn't really there, meaning this Q is really a zero. It's just zeros. It's not there. The Kalman filter will be a weighted least sum solution. And it gets done recursively in this sort of sequenced way. If your state is just some constant, it really doesn't change from time to time, so that this W doesn't exist, and this phi is just the identity. Your next time step K plus 1 is the same as it was at the previous time step. It's a constant. So if X is a constant, the phi will be the identity, and the Q will be zero. With that, let's do a few examples that are like simple, but you can address them in a Kalman filter type way. Remember we did this problem at the start of this module. We have this unknown X. It could be random, but once it's drawn, it just stays constant. And then we take a whole bunch of measurements of it. Over K, every K time steps. At each K, we get a new measurement, and we know its variance. Variance of the error of that measurement. And it's also zero mean. I guess I should put that in here. Well, that was just part of the problem statement. This error is zero mean. So we could set this up as a Kalman filter. Previously, we kind of did it the hard way. We used scalar algebra and scalar calculus to come up with the answer. But if this x is a constant, like I just said, phi is the identity, and since it's just scalar, the phi is just 1. And the w goes away. So, the x k plus 1 is just the same as x and k. So the q is 0 too. So what we're doing is first we got to set up the system model to match the Kalman filter system model. And how is the z? The z just measures the x, so h is also 1. And the v, the noise, we know its variance, so we know the R of our Kalman filter. We know all the key parameters of the Kalman filter. What do we need up here? Phi, H, Q, and R. Phi, H, Q, R. We've got them. Now we can crank through these equations. So if you keep these equations in your hip pocket, you could do all this. I'm not going to go through it here, but these are just the equations from the previous chart. In this case, it simplifies a lot because we got ones and zeros here. And anyway, what you ultimately get is this way to correct an estimate and its covariance matrix is what we got the hard. This took us quite a bit of doing when we did it the first time through. Now, if we know about Kalman filters, we can do it all on one page. Here's a problem I had from an old exam. We have this, I guess it's an autoregressive moving average problem. Very simple one. And what we measure is y of k plus some noise term. So that's our measurement model. And that measurement error, the mean is 0. That's good. We know its variance. And it's a white sequence or independent sample. So it matches our Kalman filter type setup. Our job is to estimate the A and B. This is a system identification problem. We can do it sequentially or recursively now. As we keep getting more data, we can keep cranking out better and better estimates. So write the state we're trying to estimate. By the way, as we go through this, not a single student got this problem completely right. So you know the problem, so what's the state? It should be easy. We're supposed to estimate A and B. That's our X, this little 2-element vector, A and B. And they're constants. So our Q is 0, and our phi is the identity matrix, just like in the previous example. Although this is now not a scalar, it's a 2-dimensional vector. So that's the state X. We know the phi now is identity matrix. The Q is 0. What's H going to be? We have Z equals something. Our state is A and B. So H ought to be this little row vector of the Y sub k minus 1 and U sub k. And the R should be easy. The R is just. I thought this was a super easy problem, and not a single student got it completely correct. And this was not even cranked through any equations, just set up the system model. There we go. There's our state. It's just A and B. They're constants. Here's our measurement equation, H. Here it is, sort of as one scalar line. If you set it up with our state vector here, it's just this. So that's what our H is. So phi is the identity matrix, Q is the zero matrix, H is that, and R is just the noise variance, the variance of this V, measurement errors. Don't overthink these problems though too much. We're going to do one more from an old exam. We start with estimates of X and Y, and they're zero mean estimates. So the errors in them are zero mean. The standard deviations, we know the standard deviations of those going into it, 1 and 2. And the correlation coefficient between them, we know that too. It's a half. Okay. Now, with all that starting, we get an independent measurement of Y. And we know the standard deviation of that measurement is 1. The estimates of both X and Y are then updated in an optimal manner, meaning minimum mean square error. Variance of X after they update, and what is the correlation coefficient after that update? Think about this. And now you know we want to use Kalman filter type. There's no time stepping here. We have a before covariance, and we're looking for the after covariance. Simply a problem of we have a covariance before we got a measurement, and then we're interested in the covariance after we get a measurement. So let's set that up. Here was the before measurement. This is just a 2 by 2. So its covariance matrix is going to look like this. And we're given all these numbers. So here's our before covariance. To get the after covariance, well, we're going to need the K. And we have an equation for that. And so let's see. What is H here? If we do it in this order, X and Y, that's our little vector, X over Y. And then the H, what we measured Y, so the H is this 0, 1. The R is the error of the measurement error, and that was just, I think, everything we needed, right? For the K, we needed the P before going in, got that. H, got that. And the R, we got that. We got everything we need. We just need to do this matrix arithmetic. It might be slightly painful, and I'm not going to go through all the matrix arithmetic. I'm really interested in, could you set the problem up right? Because after that, you're just doing some matrix arithmetic. As bad as this looks, let's see. P with the minus sign HT, that's a simple matrix multiply. This, we can do that easy enough. I'm not going to go through this. But finally, you get, here's the P afterwards. And what did it really ask? What's the variance of X after the update, and what's the correlation coefficient after the update? This is the variance of X. Here's the variance of Y. They're both the same. So the variance of X is just that 4/5. These off-diagonal terms are this. The correlation coefficient and sigma X, sigma Y. Sigma X and sigma Y are the square roots of these main diagonal terms. And we're trying to solve for the row. We know when you multiply this out, the answer is 1/5. So we can solve for rho. So there's the correlation coefficient. That's how we did that problem. We used Kalman filter equations to do what looked like a pretty, you probably wouldn't have known how to set this up. like some other hard way from other, trying to use probability some other way. Once you set it up as a Kalman filter type problem, it's pretty straightforward. That's what I'll say there. I'll leave something because you might have noticed we didn't tell you how to really start this filter. We told you kind of like once it's going, how to keep chunking along. Let me save that for another